Let's spend some time talking about recursive functions. A recursive function solves a problem through repetition by calling on itself to solve a subset of the problem. Recursion is one of the hardest concepts that new programmers are asked to comprehend. But if you keep three things in mind, you might have an easier time grasping this. First, that every recursive function needs to know how to solve the smallest problem. That's called the base case. Second, and this is the crazy one, is that as we write the recursive function, we assume that we've already written the recursive function and that it does what it's supposed to do. Third is that recursive functions are lazy. They get someone else to do most of the work, they do the last bit, and they take all the credit. One thing to note is that we said that a recursive function solves a problem through repetition. That sounds like a loop, and in fact, any recursive function that we write could have been written as a non-recursive loop. We want to be careful writing recursive functions because they're very resource intensive. So generally we should write a loop if we can, but there are cases where recursive functions make your code a lot more clear, and it's worth the added overhead. So let's consider a task of reversing a string. We want to write a function that will take the word, say, Python, and reverse the order of the letters. And instead of thinking of writing this as a computer program, let's think of a bunch of twin brothers who are going to solve this task. First, we said we need a base case. In this case, the base case would be a single letter string, like Q. If we're given the letter Q and asked to reverse it, well, the answer is easy. It's just Q. Every one of these twins knows that. The second thing that we were asked to remember is that we're going to assume that we've already written the function. In this case, if one of these brothers is asked to reverse a string, he assumes that all the other twins know how to do that as well. And the third thing that we were asked to remember is that all these brothers are lazy. They only want to do the last bit of the job and then they want to take all the credit. So how does this work? Well, we hand the word Python to this first brother here. He's lazy, so he says, how can I get my brother to do most of the work? Well, I'm going to hold on to the letter N because I know that belongs at the beginning of my reversed word, and I'm just going to hand the rest of it off to my brother here. Pytho. And of course, what does the brother say? He says, I'm lazy. I only want to do part of this job. I'm going to take the O, I know it belongs at the beginning of this word, and I'm going to hand the rest off to my brother. Pyth. Of course, this brother finds another brother, hands off Pyt, who hands off Py, who finally hands off just the letter P to the last brother. The last brother says, hey, I know what to do with this. I'm going to take the P and hand it back to my brother. This brother says, I know what to do with that. I just have to take the string that I was given, add the Y to the beginning, and hand it off to my brother. Notice, this brother asked for Py reversed, and he got it back. Now this brother says, all I need to do my job is add the T to the front. Pass it off to my brother, who says, all I need to do my job is add the H to the front. Pass it off to my brother, who says, I just need to add the O to the front. Pass it off to my brother, who says, all I need to do to finish my job is add the N to the front and give it back to the user. So notice this brother took all the credit. He provided the final answer, but he only did one little bit of the job, the last part. Each brother assumed that if they handed part of the problem off to their twin, that they would get the correct answer to that part of the problem back. The last brother was assigned the base case, one character, and all he had to do was return the same character back. And this is how recursive functions work. Let's code up this exact problem in Python. So we're going to code up reverse a string, and we're going to ask it to reverse the word Python, just like our example. Look, I'm already assuming that I wrote this function. If we keep our important three concepts in mind, you're going to be blown away at how easy it is to write this function. Our function accepts a string as a parameter. We'll write a docstring here. The first thing we were told to remember is that we have to provide a base case. What does the very last function in the recursive process do? In the case of reverse a string, if it receives a single letter, it just returns that single letter. Easy enough. Now, if it got a bigger job to do, remember we're saying this recursive function is very lazy. It's just going to do the last part of the job. It's going to tell someone else to do the rest of the job. And finally, remember that we assume that we've already written this function and it does what it's supposed to do. I could do this all in a one-line return statement, and I'll do that at the end, but I'm going to write a few extra lines at first to make this more clear. Remember with our twins, each twin hung on to the last letter of the string, and that became the first letter of the return string. So let's say first letter equals the last letter of the input string. Remember that -1 as an index gives you the last character of a string. Next, we're going to take the rest of the string and assume that there's someone else who knows how to do this job. We're assuming that we've already written this function and that it works. The argument we're going to pass is a slice. We're going to pass the string right up to the last character. When we go to return a string, we just put those two things together. And that's it. I need a colon here. Let's tighten this up and run the program. And there we are. How amazing is this step? That we don't have to think about what all the lower levels are doing. We just assume they already know how to do their job. And if we do this, if we provide the base case, and then assume the function is already written and does its job correctly, then the answer comes like magic. Let's write one more just for practice. Let's write a recursive function that tells us the nth Fibonacci number. The Fibonacci numbers are 1, 1, 2, 3, 5, 8, 13, 21, and so on, where each number in the sequence is the sum of the previous two numbers. This is an interesting one for recursion. So we're asking for the nth Fibonacci number. I'm using the letter n here. That seems like a non-descriptive variable, but in fact, since in math we talk about the nth Fibonacci number, n is probably a good variable to use. This problem is interesting because we have to write two base cases. Remember that each number is the sum of the two previous numbers. So if we're dealing with Fibonacci number 0, obviously there are no two previous numbers. That's going to be a base case. But also when n equals 1, we only have one previous number, so we need to hard code that response as well. But fortunately we get the same response for either, so we'll say if n is less than or equal to 1, return 1. That takes care of the two base cases. Now another interesting feature of this function is that we're going to have to do two recursive calls for every call to the function. So if we're asked for Fibonacci number 2, we need to call Fibonacci number 1 and 0 to get the result. This time I'm going to write the whole return in one line. Again, notice, I'm assuming I've already written the Fibonacci function, and I'm just calling that function with n-1 and n-2. If I'm asking for Fibonacci number 5, that would be 0, 1, 2, 3, 4, 5. The answer should be 8, and we'll get that answer by asking for Fibonacci number 4 and 3. That's our function, believe it or not. We'll add a docstring. If you don't like thinking of this one as the 0th Fibonacci number, you could rewrite this function a little bit. Let's make sure it works. Let's ask for the 7th Fibonacci number. And let's see what we expect. This is 0, 1, 2, 3, 4, 5, 6, 7. We're expecting 21 to come out. Let's see if it does. Perfect. Now, I said that recursive functions can be very resource intensive. This particular one is really bad because every time it's called, it spawns two more Fibonacci functions. And that can get out of control really fast. Let's ask for Fibonacci number 20. And let's ask for 30. Took a little longer. Let's ask for 35. Took quite a bit longer. And very quickly we find that we can't wait long enough for this function to finish its work. I'm ending this because I hear my fan spinning up and my computer is working really hard. So notice one feature of both of the functions that we wrote. Each function is passing a little bit of data down to the next one. They're not using any kind of global objects. And in general, if you're using a global object to solve a problem, you're probably not solving it recursively. There may be some exceptions, but please keep that in mind. Also, with each function, we're passing a smaller and smaller problem to the next function. In the case of Fibonacci, we're passing a smaller number each time. In the case of reverse a string, we're passing a smaller string each time. In general, each pass to the next function should be getting always one step closer to the answer. If you're not passing a smaller subset of the problem in each recursion, then your function may not truly be recursive. And that's it. I'm going to leave you with a quote, and that's that you can't understand recursion until you understand recursion.